All right, somebody tell me what they got here. What did you get for your next step? No, we got rid of the dichromate. There's no more dichromate. Actually, let's try it.
The result is the complex.
So what is it? What's the next reaction? What's going to be attacked in that mixture by potassium oxalate? The chromium-3. So the chromium-3 gets attacked by how many oxalates? How many oxalates can bind to chromium-3? No. Are you just copying the
Oxalate minus 1. Minus 2. Yeah. So 2.
No, you got to think in terms of coordination number. What is the coordination number of chromium-3? 6. And so how many oxalates can we bind?
3.
3. We're going to attack it with 3, and that's going to form...
2, 4, 3.
And the charge on this is... chromium is plus 3. The 3 oxalates is minus 6, so it's minus 3, right? That's minus 3. What kind of reaction is this? Well, we draw this out like this. Chromium-3, an oxalate. We already did this, didn't we? Okay. Boom. Right? This is a Lewis acid-base reaction. That's correct. And so we attach one of these. Sometimes they do this, you know. To make it a little easier, they use these organic type deals where they don't show the carbons, they just show kinks where the carbons should be. Have you seen that in organic chemistry? There's a line drawing like this.
Draw zigzag lines of carbon.
Yeah, zigzag lines representing each kink represents a carbon. And so sometimes we can leave out the carbon like that, or we can include it. It doesn't matter. But you should include it first, so you know the proper way to do it. And so that's one, but chromium can be a octahedral. It's still 3+, right? And the oxalate's still, you know, minus. Even though technically, we just count it funny. Remember? So the oxalate's 2-. So how many more can we attack here? 2 more, because the coordination number on chromium is 6. And what kind of complex do we form? What kind of complex is that?
Is it octahedral?
It's octahedral. In an octahedral complex, do you think the oxalates bind to adjacent positions or opposite positions? Adjacent would be a 90, opposite would be 180. And the opposite is too far.
We can't do it.
The 3 oxalates have to bind to adjacent. This one I'll write out. How about that? I'm going to write the carbons in there. Done.
Wait, do we have to draw it out?
So this is... Do you have to draw it out? You know, I sometimes people write papers and they don't know what to fill the paper with, right? Because they come up blank, you know. And so, like, some simple things like writing out the chemical equation, people don't want to do because either they think it's too much work or it's unimportant. And so, let me tell you this. If I got a paper in which somebody drew it out versus a paper in which they showed nothing, what do you think I would like better?
Nothing.
Nothing? Nothing shows me that they don't really know much, right? So if you know a lot and you think, I know this, but you know what? I'm not gonna say anything. I'm not gonna draw it out. I'm not gonna do anything. Then I have no, you know, people come up to me after the test and said, I knew that, right? But, you know, they didn't do anything. They didn't write it. They didn't show anything. I can't give them credit. Even though they could, probably they knew it, you know, during the test. Well, what do you think? I'm a mind reader or something? You know?
Yes, we must.
And so, you know, people think, oh, it's ridiculous. Everybody knows that. Well, then just say it, you know, because the target audience for this is, you know, other students in the class. Do you think they'll know it? Maybe, maybe not. You know? You can say, oh, you know this, so I don't have to write anything because you already know what's happening here. So, no, that's not the point. Scott?
Why do those oxygens have a negative formal charge?
They shouldn't, right? If we're counting formal charge properly, those oxygens are screwed up. But this is just the way we count the charge. When we count the charge here, we don't worry about those formal charges go down to 0 because this is a covalent bond. We still treat it as ionic, so this would be chromium 3+, and those each oxalate would be -2. Even though in this, you're thinking those are covalent bonds. Charges have shifted totally,
Why
right?
does he put in the upper right? The negative.
Up here,
Is that because of the oxalate is 2-?
oxalate is 2-. The whole thing is 2-. Right, or I could just write the, you know, I could, although I don't know if the, you know, I could just write the 2- like that, you know. But oxalate's 2-, you know, so it's, I told you early on, you don't count them like you normally do, so it looks weird. But this is the convention that they use for complexes. This, you know, I'll tell you, this has always bugged me. It bugs me because it's a covalent bond, but these oxygens should no longer carry formal charge, and that chromium's charge should go down, right?
Yeah.
But and it's got to happen, you know. Oxygen's losing negative charge density to chromium, right? It's got to happen, especially if this is a covalent bond. But I think somebody, you know, decided that this would make your life easier if you don't have to worry about this kind of stuff. But does it really make your life easier? You know, you spend all this time learning the rules for counting formal charge and oxidation state, and all of a sudden they screw it up like this. This is not accurate. You know, it's not accurate because, you know what, I think whoever formulated these rules thought this. One, it's a lot easier not having to work it. True, it's a lot easier, right? It's a lot easier not having to worry about the coordinate covalent bond. Just treat it the same as before. But 3, you know, that's only for counting. You know, our understanding of the bonding is going to be screwed up then. So which one's more significant? Understanding the bonding or coming up with some fake numbering system? Well, the fake numbering system is always the case. I mean, it's always a fake numbering system. But anyway, the rules don't apply for complexes. So we'll leave it at that.
That was a good question anyway, Scott.
Yes. That's good, because somebody who knows that will automatically see that these numbers don't make sense. But nonetheless, we're going to count it like this. The chromium is a 3+, and each oxalate is a 2-. And so the 3+ minus 6 gives us the net charge of -3. how would we do it otherwise? How we do it otherwise is we count the formal charge as normal. You know, how many valence electrons does chromium have? Chromium 3 plus have. How many valence electrons does chromium 3 plus have? Somebody tell me, how many valence electrons does chromium 3 plus have? Chromium 3 plus. Oh, it loses 1, it's like this. It loses 2, it's like this. It loses 3, it's like this. So is it 2 valence electrons? The 1, 2, 3, 4s, 2 valence electrons? This is let me when I'm asking you this is testing your Chem 1A knowledge. How many valence electrons does chromium 3 plus have? That's in chapter 10, or isn't that chapter 9?
Two.
It's 0. It has 0 valence electrons. Well, anyway, this is why I say, you know, review your Chem 1A, you know, repeatedly so you don't forget this stuff, because when you form a transition metal cation, what gets ionized first, the S or the D? The 4s or the 3D get ionized first when you form a transition metal cation. The 4s get ionized first. You lost those. And the 3D are considered not valence. The 3D are considered inner shell or core electrons. Okay? That's important here because, no, I didn't write any dots here. If they had 3 valence electrons, I should have written 3 dots here, right? It's got no valence electrons, so there's no dots there. And so where are those d electrons? We don't show those because those are in the inner shell. Those inner shell ones actually don't participate in the bonding. So anyway, this whole thing carries a net -3 charge. Okay, we're not done yet because potassium salts are all water soluble. So if you said you were forming this potassium whatever, okay, that's okay, but in reality we got potassium ions and this complex, they're separate. We got to bring them together. How do we bring them together? Well, one way to bring a soluble salt together is to evaporate all the water, right? Just evaporate the water. Oh, I didn't talk about one thing. What about all that excess oxalic acid? What about all that excess oxalic acid? What's happening with that? Well, you know what? Oxalic acid contains, oxalate. And so this reaction can happen right away. And that is chromium 3 doesn't have to react with potassium oxalate. It could also react with oxalic acid. Now, it depends on what's better, having a hydrogen covalently bonded to oxalate or having a chromium 3 covalently bonded to oxalate. And what do you think is stronger? Okay, that's actually to the chromium 3 plus, and then what else is going to form? CO2, no, there's no CO2 in this one. No water. Not hydrogen gas. This is just an acid-base reaction. This is Lewis acid base. Almost like a, what's the other product that forms here? Oh, what's left over? 6H pluses. Oh, did you?
Yeah, I said that first. You said no.
Oh, I thought you said.
That's why I went on to hydrogen gas. So.
Oh, okay, I missed that then. I just heard hydrogen gas, so sorry. You're right then. 6H pluses, or H plus forms. Actually, both of these can do the same thing, because both contain oxalate, right? Potassium oxalate and oxalic acid. And oxalate's a good ligand. So this is what screws up the stoichiometry problem in the book, because it doesn't take into account the, it treats the problem in the book is, the reaction in the book is it treats the oxalic acid and the oxalate as doing two totally different things. They can't do the same thing. And so that's why, as I mentioned earlier, I don't like the way it's written in the book. Because then people, when people calculate the limiting reagent, well, they'll see, oh, it's the oxalate that's the limiting reagent, or was it? Or the oxalic acid is the limiting reagent, not the dichromate. Actually, did anybody do that? The calculation for the limiting reagent? Okay, now this is the next reaction here. So what we formed is we formed this complex anion, but what do we have to do next? The next reaction is like this. The next reaction is, this is like, I want solid sodium chloride. All I have is salt water. How can I get solid sodium chloride out of salt water? Yeah, evaporate the water, right? Evaporate the water. I want big crystals of sodium chloride. Should I evaporate the water rapidly, or should I evaporate it slowly? Slowly, so that the crystals can grow, right? So what we want to do is we want to bring the ions together. When we have the ions come together, what kind of reaction is that? Metathesis. So that's the word I was looking for. This could be, this could be either be considered a metathesis reaction or just a physical process, crystallization, we call it, right? But we'll call it metathesis because we want to bring the ions together. What ions do we want to bring together? We want to bring potassium ions and what do we call this ion? Yeah, and then we want to get how many waters stuck in that lattice? 3 for every formula unit. So we got to bring all these species together and get them to form nice crystals, right? Well, the problem is if we evaporate the water, what else is going to happen? No, if we evaporate the water, then the ions are forced to come together, right? And the ions will come together, but we have other junk in there. What's the other stuff we got in there? We got excess. Well, the carbon dioxide bubbles out. There's a gap. Well, the H+, okay, we can probably deal with those, but those will probably combine with oxalates, and form oxalic acid, right? H++ oxalate gives us oxalic acid. The problem is the excess oxalic acid. Excess oxalic acid, when you evaporate the water, you're going to get, you know what color oxalic acid is? White. You're going to get white crystals contaminating your, you'll see, something like that. Right. They're like purple, black crystals. You don't want that, do you?
No.
No. No. So what we have to do is we do something called a separation. We need to separate this stuff from everything else. There are different ways we can do a separation, though. But the problem is any way we try to crystallize this or precipitate this out will precipitate the oxalic acid too. And so how can we get this stuff to precipitate without the oxalic acid precipitating? And then the way we're going to do that is we're going to use a technique that's quite common in synthesis and organic chemistry. And that is, we're going to rely on the differences in solubility based on solvents. And so oxalic acid and potassium trioxylchromate 3 are both highly soluble in water. But what we're going to do is we're going to change the solvent from water to ethanol. Because it turns out that oxalic acid is much more soluble in ethanol than this stuff. In fact, this stuff isn't very soluble in ethanol. This stuff is very polar and prefers water. And so, well, how do you change the solvent? You can't just say, okay, it's not like changing a shirt or something like that. How do you change the solvent? I got a bunch of water in there. Now I want ethanol.
Well,
You got it, Kelly? How?
you gotta evaporate all the water. And then, like...
Oh, that's one way. We could evaporate all the water and then just dump in ethanol. But we aren't going to do that because there's a much easier way. Much easier way. How do we change it? The way we're going to change it is we're going to rely on, you know what an ideal solution is? Somebody remind me what an ideal solution is. Well, one of the things about ideal solution is they got to mix in. In fact, I gave a demo of an ideal solution in Chem 1A. Does anybody remember that? Water and water, right. Water and water form an ideal solution. Although it's kind of ridiculous. But, you know, is there any limit to how much water I can mix with water? No. This is what we call infinitely soluble, or there's another word for it that starts with an M. Does anybody remember that word that starts with an M?
Yeah.
What? Miscible. That's it. You remember that. Miscible. Have you heard that word before?
Yes.
Yeah. Okay, good. And so this is ridiculous because water and water, of course they're going to mix in all proportions. But you know something else that's miscible? Water and ethanol. Water and ethanol are miscible in each other. And so that gives us our way to do it. The way we change the solvent is this. You know, usually we call the solvent the species with the larger quantity, and the solute the species with the smaller, present in smaller quantities. And so all we do is, if we have a bunch of water like this, then I'll just take a whole bunch of ethanol, and I'll just keep adding ethanol until it becomes all ethanol. You know, and so if I have a water like this and a tanker full of ethanol, you know, and I dump all that, or I dump this in, then it's no longer water. It's going to be
Ethanol.
It's like going to be like ethanol. And so what we're going to do is we're going to just do the solvent exchange. So what we're going to do is we're just going to keep adding ethanol. As we increase the amount of ethanol, then it's going to be more ethanol-like, less water-like. And then what should happen is that, well, this stuff doesn't really like being dissolved in ethanol, and we should precipitate it. And so this is a very tricky metathesis reaction in the sense that now all that other stuff should stay dissolved, like that excess oxalic acid that stays dissolved. And then what we can do is we're going to filter this, right? And then wash the crystals off, because we've got to wash any kind of contamination on the surface of the crystals. But in the process of doing this, what we want to do is we want to get big crystals. We want big crystals. And so, do you guys know about growing crystals? When you grow crystals, there are two processes that we have to worry about. One is called nucleation. You know, nucleation is just like the birth of a little crystal. You know, one ion binds to another ion kind of thing. And it just starts a tiny, tiny baby crystal. And those baby crystals grow, right? And so those baby crystals grow into bigger crystals. And so it's called nucleation and growth. The situation here is, if you want big crystals, do you want to nucleate a whole bunch of baby crystals, or do you want to nucleate just a few baby crystals? Or just one? Ideally, one would be nice, and then we get one gigantic crystal, right? And so what we want to do is we want to minimize nucleation. We want to minimize this. There are ways, people try to promote nucleation. They promote nucleation by adding seed crystals, or like those people who try to seed rain clouds, They seed rain clouds by putting little particles in the air so that the water can start to nucleate into a droplet, right? That kind of thing. And then hopefully grow big enough to precipitate. Well, we got nucleation. We want to maximize growth. And so some of the things, slow is better than fast. When you do it fast, some people dump all the ethanol at once. And how much ethanol do you need? This is where you got to start thinking. You got to start thinking, because some people say, oh, I've added all the ethanol, but I haven't gotten any crystals. What should I do? Well, what would you do? Just give up? Well, the book says to add this much ethanol. I'm going to give up now. Well, no, what would you do? Add more ethanol. You just keep adding until you maximize the growth, until you maximize the precipitation, right? So this is what I mean by altering the procedure. On the other hand, let's say you maximize it with half as much, and if you keep adding, it doesn't look like anything else is happening. Well, then stop, because you're just complicating things for later, because you got to clean all that. Well, ethanol is easy to clean off anyway, and so we got to think about it. And so anyway, think about that, and then we filter and then clean the crystals, right? And so there are questions that we always can ponder. After we go through all these steps, how pure are my crystals? Are they 100% pure?
Depends on how big they are.
What would you say? If they're millimeter size, are they 100% pure?
No.
If they're 10 millimeters, 100% pure? What's the cutoff? Let's say 10 millimeters is 100, 9 millimeters is 90%, 8 millimeters is 80%. Is that how you would do the cutoffs? Well, one of the things is we got to think about our starting materials. How pure was the potassium oxalate, potassium dichromate, and oxalic acid that we started with? Well, there are different grades we can buy. What do you think we buy? The expensive stuff or the cheaper stuff?
I'm going for this.
We gotta buy the cheaper stuff. The expensive stuff is too expensive, right? This expensive stuff is called analytical grade, or analytical grade is very high purity.
Is it like 99% pure at that level?
Well, it's more than that. They give it nines, like 6 nines purity, or like 99.9999%, something like that.
Wow.
Depends on how much. Or you buy helium. When you go buy helium for a balloon, do you think it's 100% pure? No. We buy helium here, we get 6 nines, 99.9999% pure helium. It's like, 1,000 times more expensive, something like that. Because they have to purify it. It's not easy. And so what we buy is technical grade, which is like 98%. 97%, 98%, maybe 99%, depends. That's technical grade. And you look at the stuff, it looks pretty good, but there are impurities in there. And so usually they give you a spec sheet on the impurities. But most of those impurities aren't going to screw with us, and we'll be able to wash those off or filter them out, like wash them with a supernatant. Yeah. And hopefully our stuff is pure at the end. But we got to think about how you can be so sure, because if somebody came back to you and said, well, you got some nice crystals there, but how pure are they? And then, well, you might say, I don't know, but they're nice crystals, aren't they? Anyway, well, that's not usually good enough in science, because in science we need to know a little more, about and what kind of impurities you expect. So you pay more attention to things, because things, it's nice when you do Chem 1A reaction and you get these as the products, but when you actually do the synthesis, you get a whole bunch of garbage in there. that people start to worry about all that garbage, you know. And the garbage for silicon wafers is very important because if you get one contaminant atom in there, you know, the chips are going so small, they got to toss it, you know. Well, anyway, I'm going to stop here. Maybe I'll talk about one thing. You know, space shuttle. You know, this is a classic story. Although I never read the original, but I was told this at a conference. The space shuttle, they're trying to grow high purity wafers up there. You know, not silicon, but some others like gallium arsenide or something else up there. And so they thought in the space it's going to be great because, you know, in space you can get much higher vacuum than you can get on Earth. Right? Vacuums, you just suck out everything, you know, so you just have left with empty space, right? And so they tried to grow these ultra high purity crystals, you know, by making some kind of arm that goes off the space shuttle and growing them out in space, you know, which has fewer you know, particles, whatever. But they brought them back, and they were much more contaminated than the ones they grew on Earth. And that's because the space shuttle was degassing all kinds of impurities off. Something like that. Anyway, I'll stop here, and then we're going to get started. So you're going to work on this